Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, grade 9, so what we're going to do is we're going to move on now to a little bit of what would be classed as physics in the subject of physical sciences, moving on to grade 10, 11, and 12, of course. And we're going to just introduce forces right now, and we're going to have a look at two types of forces, okay? Two subcategories of forces that do lead to obviously more specific types of forces. If we look on the left, contact forces, what we're going to have a look at with regards to contact forces are friction, tension, and compression. And then with field forces, we'll be having a look at the gravitational force, magnetic force, and electrostatic force as well, just as a bit of an introduction, okay? So when it comes to types of forces, we must understand that there is force that exists around us all the time, all right? You will use force in everything that you do, all right? And the two types of main movements that we as humans do are push as well as pull. All right, those are like the main two types of forces that we would get, or movements rather, that we as humans do. We either push or we are pulling in some way, shape, or form. Okay, force is even applied to the simple recreational activity otherwise known as sleeping. All right, there's even forces that exist when you sleep. All right, and for example, you might ask, what types of forces are those? Well, those types of forces, they move your chest up and down when you breathe, because when you sleep, you don't just shut down entirely. Shut down would be the incorrect term there, but of course, you're still breathing, and those forces are obviously pushing your chest up and down to show that there is movement of air flowing into your lungs, etc., etc. Okay? So it would be safe to assume that forces, all right, would be needed to start moving, all right, things. So a force would be required to start moving an object, all right, whatever particular object it may be, but also be needed to stop the object as well, or stopping the object. In other words, just slowing the object down. Changing direction as well as changing shape. We especially see that with in the field of engineering or construction, all right, using a sledgehammer or just a hammer in general, changing the shape of steel, knocking something into place or knocking something out, all right. Those are forces, of course. As I mentioned, forces are pushes or pulls, all right, that can make an object change its state, phase, all right, or even rest or motion, the difference between rest or motion. Okay, now we obviously all know that push and pull have the opposite effects. Okay, we see that some doors require us to push while others requires us to pull, and I always get this wrong. I don't know if I just can't read a sign, but often I try one of those two first before I actually read what the sign was. So sometimes I try pull first when the sign actually says push, and I actually never care to read it first before I actually approach the door. That's it's very silly of me, but anyway. What was I saying? Yes. Both of those are contact forces though, because when you pull a door open, you obviously pull it by the handle, you've made contact with the object. And obviously when you push a door open as well, the same thing. Sometimes you may push a door closed even, or even push or pull a door closed as well, depending on which one was, because both of them work the opposite. Sorry about this. Press the tablet little button there. Okay. One thing we must understand with regards to forces is what it is measured in, okay? So forces, all right, or force rather, let me just take the S out. Force is measured in a symbol, okay, when we calculate it, okay? Force is measured in newtons. right? Forces is measured in newtons. Okay, a guy by the name of Sir Isaac Newton discovered all these forces, or discovered force or studied force as a law in the realm of physics and realms of science. And in grade 10, he learned about the different laws that he came up with. He came up with about actually four laws, but his fourth one has a specific name, but otherwise his first three are just called 1, 2, and 3. Okay, and it's measured in newtons, and the symbol for it is capital N. Okay, newtons, because obviously the guy who came up with the concept of force, of course, is Sir Isaac Newton, so we just use his surname. Okay, and he was an English scientist, by the way. Probably when you are in class, your own teachers will tell you a bit more about him. Obviously, it's not physics. It's not a history lesson. Okay, so, and even in the subject of history, we don't even have a look at scientists and what they did necessarily. Okay. One thing about a force that you must understand, grade 9s, is that if a force is exerted in one direction, there will always be an opposite force, okay, that will react to the first force. Okay, but it will always be opposite. If it's an opposite force, it means it's going also in the opposite direction. Okay. Now, all these forces that we're talking about, we've placed them into two very broad groups known as contact forces, as also known as field forces. Another word for field force is also non-contact forces. All right. Gravity will exist on the Earth if nobody had to be on the Earth. Okay, so it's considered a non-contact force. The result of gravity is that our feet touch the ground. It's just a result of gravity, but it's a non-contact force. It doesn't really make contact with us. So the first thing we're going to have a look at is contact forces. All right, and then we'll take a look at see here, what do we got? We'll take a look at some field forces if we have enough time, and then we'll see if we can find a little bit of an activity that we can do to consolidate all this work. All right, we may not, but we will try. Okay, a lot of the activities that I see here are basically little steps or little practical things to do, but I don't even think you teachers, if they had what I have now, would require you to do most of these things. Okay, so let's just go and first let me find my page. I don't know where my page is. Let's go have a look at contact forces quickly. Let me just clear the board. Okay, and we just get our heading down here. Contact forces. Cool. Okay. Now, with contact forces, okay, as you've seen the mind map, okay, friction, tension, and compression, all that kind of stuff. Okay, when two forces touch one another, they are, of course, in contact, and the result will have a contact force. Okay, so we have contact forces when two forces touch one another. These forces will include push and pull, as often as it happens between two children. Okay, so for example, two children pulling a rope. Okay, and obviously pulling a rope that is okay, I'll get back to that. Okay, so two children, okay, pulling a rope, okay, or pushing a rope. No, you can't push a rope, but possibly pushing. What else can two children push? Oh, say pushing a swing. Okay, contact force. Okay, this could also be called mechanical force. Okay, so also add that word here. Also be called mechanical force. The notion of push and pull happening together. So, it is a physical force where energy is exerted in either pushing or pulling. Okay, so let me just add a cursive F there, force. Yeah, if I still remember how to write cursive. Okay, physical force, the definition there, where energy is exerted in either pushing or pulling. Okay. If a lever is used to move something heavy, it is also called a mechanical force. Okay. Now I want to introduce two other forces by the names of friction . Okay, let's have a look at friction. Now friction, usually an example of that would be an eraser rubbing out a pencil or rubbing out pencil markings or pencil line. Okay, when we were younger, we were always taught to write in pencil first, and then when we got a bit older, we moved to writing in pen. Okay, but friction obviously occurs when you rub it between the, obviously if you feel the page after you rubbing out your pencil, especially if you're rubbing out quite hard, all right, you will know that feel that there's a bit of heat there. Okay, that's an example of friction. Okay, but friction is also the name given to the force in the opposite direction. I spelled opposite wrong. Okay, also the force given in the opposite direction. So if you take a look at a car that is pulling off, all right, you'll find that the car will leave behind some tire marks if he accelerates quite fast off the mark, right? That's a result of friction, all right? That's a result of friction because the markings always look like it's gone backwards as the car is moving forwards. Okay, the tire marks don't appear in front of the car, they appear behind the car. Okay, that's friction. I'll give you guys some time to get that down. The next type of force, which is also a contact force, is tension. Okay, now if you have a look at tension, if you example on a rope. Okay, if we have a look at example tension that's on a rope, such as one car towing another car, one car towing another car, so it's pulling another car that is broken down. Okay, you'll find that there is tension on that rope. All right, on a rope, one car pulling another car. So you obviously have the one car here, which I'm just going to draw like in a little block type feature. And there's the rope in the middle. And then there is obviously the other car. Okay, so let's call that car A. Let's call this car B. Now you see how straight I've drawn the line, because that's how straight the tension in the rope is going to be, or the rope is going to be. It's going to be very tight. All right, very, very tight. So that is tension. All right, it's almost as if the rope, if there's too much tension, the rope will snap. Okay, but the tension being like it's stretched out completely, and it's trying to keep obviously the two cars connected with that. You know, the rope is trying to keep the two cars connected with the force of tension. But if there's too much tension, of course, it can snap. Okay, so that's why we don't want to create too much tension. So the car A can't weigh less than car B. It must weigh either the same or slightly more. Alright, because if it weighs a bit, because if car A weighs less than car B, so in other words, a normal Polo Vivo trying to pull a gigantic truck, it's just not going to work. It doesn't make sense. The tension force of tension will be so much that it will cause the rope to snap. Now that's tension. And then we get another type of compression force, which is known of contact force. Sorry, I've given it away, which is known as compression. Okay, compression force meaning could be when you're squeezing. So you're squeezing a stress ball or tennis ball, depending on how strong your hand is. Okay, that would be, of course, a force of compression, and that'll also be a contact force as well. Okay, so I'm not going to get you guys to do any activity on this, all right, to kind of see. But I mean, obviously, if you take a towel, even may not have a rope, but if you take a towel and you pull on it pull both ends of a short little towel, or even a longer towel, you will obviously see that tension is obviously keeping that towel quite tightly together, unless you pull so fast that or so hard that you overcome the force of tension and you cause the towel to break or tear, so you just rip it in half. Okay, if you do, you like flipping Hercules and you're super strong. Okay, good job. Otherwise, that's it on contact forces. Okay, cool. So what we're going to do is we're going to shimmy on over to the other forces, which other group of forces which are known as field forces or non-contact forces. Okay, and we mentioned a bit about those. One was gravity. Okay, one was gravity or the gravitational force. Other one was a magnetic force. Okay, and we sure know how magnets work. And the other one was an electrostatic force. Okay, which obviously involves some type of electricity. Okay, some type of electricity. Okay, so we're going to learn everything with regards to this, and then we'll have a little bit of activity afterwards. Okay. Alright, let's have a look at some field forces, otherwise known as non-contact forces. Okay, so field forces, alright, as I mentioned, are forces, alright, that act at a distance between two bodies. Okay, so let's have that definition down. They act at a distance. Okay, they act at a distance between two bodies. They do include the gravitational, magnetic, and electrostatic forces. Okay, let's look at each of these, starting with the gravitational force. Okay, now this is quite a bit. Okay, so I think we're going to need to have a look at some graphical images here quickly. So let's have a look at the gravitational force. Okay, I'm sure we all know is a force that pulls. Okay, it's a force that pulls objects to the earth. Okay, it pulls objects to the earth. It is a pull force. Okay, very important to denote. It is a pull force. Okay, if you really want to know the extent of how this force pulls you, please go try skydiving. Okay, when you're older, and because you actually have to take a skydiving course, you can't just hop out of a plane. Okay. However, if you want to test it like a little bit more milder, you can obviously drop anything, and you'll see that it'll fall to the ground. Drop a tennis ball, preferably something that you don't mind dropping. Please don't drop your phone, unless your phone is crap and you want a new one and claim for the insurance. Then please go ahead and do that. Otherwise, don't do it. The bigger the difference in mass between two bodies, the bigger the force of attraction will be, which is very important to denote. Okay, let's get that part down. Is that the bigger the difference? So almost like the bigger they are, the harder they fall. Okay? In mass, between, write the number two bodies. The bigger the force of attraction will be. Alright, cool. For example, I'm sure last year in grade 8 you learned something about the solar system. Okay, the planets orbit the sun and don't fly away into space because of the force of attraction that is obviously exerted by the sun. The moon is held in an orbit around the earth because it is attracted by the larger body, which is called the earth. So even the earth, and all its gravitational force, which is obviously keeping us here and everything like that, still does the same with other planets. Okay, such as keeping the moon in an orbit, right? And the sun, which is keeping everything in the solar system connected. Obviously at a certain distance, of course, etc., etc. All right. So, let me give you guys a chance to get this down, you see, and we'll move on. Something interesting though, people and all other objects on Earth, that we are held to the Earth's surface because of the attraction or the force of attraction by the Earth against smaller objects. Okay, so this would be known more so as the gravitational pull, alright, or otherwise known as gravity. Okay, and Isaac Newton, or Sir Isaac Newton, and he was referred to as an English scientist by the title, okay, observed this under an apple tree, and an apple fell to the ground. So he observed that even an apple who gets detached from a tree falls straight down to the ground. It's a smaller object than him as a human. Okay, it's a smaller object, yet still falls to the ground. So that's called a gravitational pull. So, in other words, even though it was on the tree, gravity was still making some type of pull on it. And when it decided to release itself, or the tree decided to release the apple, bam, fell to the ground. Okay. Objects also with smaller masses will also pull on other objects, but their pull will be so small that you won't see it or feel it. Okay. If you have a look, the closer the two objects are in mass, the more equal the pull will be on both. Okay. Something very, very interesting that I'm going to denote there is that the moon, okay, which is a spectacular thing to observe in the evenings, nighttime, right? This little white sun-like spherical planet staring at us, all right? If we can actually almost see onto the moon, how the surface looks like. Very cool, very kiff. Okay. The moon affects. Okay. The moon affects tides in our ocean. Okay. If you did not know that, now you know. The moon affects tides in our oceans. All right. Why does it do that? It exerts a pull on the earth. It exerts a pull on the earth, but not as strong as the earth's pull on the moon. Alright? So the earth puts a more stronger pull on the moon, but the moon still puts a pull back, except it's not as strong. Alright? Obviously Earth being a bigger planet. Okay. Obviously we have observed a photo of Neil Armstrong. Alright? Actually the late Neil Armstrong, who passed away in 2012. Alright, he was apparently the first man to step out onto the moon's surface, and obviously the gear that those NASA scientists had on their bodies that they used, boots were very heavy, and the reason why their boots were heavy was they were used to help him hold to the moon's surface, because the gravitational pull on the moon is not as strong as what it is on Earth. It's actually a bit weaker. If I'm correct, I think, just me taking a bit of a guess, that the moon's gravitational pull, I think, is only about 6.0 meters per second squared, while Earth's is roughly estimated at 9.8 meters per second squared. So 6 compared to 9 actually makes a heck of a difference. So that's why they need to wear heavier gear, otherwise they'll almost float. They will almost float on the moon, and if you float off the moon into space, well, yeah, forget about it. You ain't coming back. And it's not cool to die in space. Well, I'm sure it's not cool to die in space. I've never died in space before. Okay, just keeping on gravity. The force of gravity will decrease as the distance between two objects increases. Okay. Apparently, in grade 7, you may have studied this planet Earth and beyond. But the closer the objects are together, the stronger the gravitational pull. So, for example, you do skydiving. You do skydiving from quite high up in the sky, of course, and you don't start falling very, very, very fast. But you do fall, of course. You do fall. And but the closer you start getting to the Earth, you start feeling a stronger pull as your height starts to decrease, right? Because the distance between you, how high you are in the sky, and obviously the Earth's surface is now getting smaller and smaller and smaller. So there's still a pull, yes, which is obviously what's pulling you down. It's not like you go to a certain height in the Earth's atmosphere and then gravity has no effect. Oh, it has an effect, right? And if you don't have a parachute, well, yeah, you're in a bit of trouble. You definitely are going to be in a bit of trouble, right? Which is something that we don't want. Okay, but that's obviously when you go skydiving. It's looks like a fun activity, something I still want to do, but I can feel that for myself. Okay, like I said, the closer you start getting to the Earth's surface, the stronger of the gravitational pull will be. Now, we use newtons, obviously, capital N, to measure the force of gravity. However, now, when you weigh yourself on a scale, you do not say that you weigh so many newtons, okay? So, when it comes to a scale, it's sometimes called, obviously, a weight scale. But the correct term should actually be called a mass scale. The reason is that when you weigh yourself, all right, when you weigh yourself, you say, hey, my weight is so many kilograms, all right? It's incorrect, okay? You don't say you weigh so many newtons when you step on a scale. You say you weigh so many kilograms, all right? For example, I step on the scale, I weigh about 96 kilograms. Or at the beginning of last year, I think I was 101 kilograms. Okay, I think now I'm about 92 or something. I lost a bit of weight. But I don't say I weigh so many newtons. I don't do that. Okay? But what's actually correct is that, so we just put this here, that we express our, and we're putting in inverted commas here, weight in kilograms. So kgs, okay? But actually weight is measured in newtons. Okay, so weight is measured in newtons. Okay, N. So just write the word here. N. Okay. So in other words, what's measured in kgs is actually not weight, but mass. Okay. When you stand on a scale, you're actually measuring your mass and not your weight. All right. The difference between mass of an object, there is a difference between the mass of an object and the weight of an object. The weight of an object is given by the following formula, which I probably might be rushing ahead maybe, but it's calculated like this. Nothing's wrong with teaching you now. Weight being a small w is equal to the mass of an object multiplied by the gravitational force. Sorry, not the gravitational force, but multiplied by the gravitational pull, or just gravity on the Earth or on the specific planet. So if you want to calculate your weight, I'm going to take the number 96. So I take the number 96 for 96 kilograms, and I decide that I want to find out what is 96 kgs in terms of weight. I'll take 96 times 9,8, and I'll get what my weight would be in newtons. Okay, but when I stand on the scale, I don't measure my weight. I measure my mass. All right, in kgs. So that's the difference between them. Okay, and I still got 10 minutes, so I can still carry on talking about this. Okay. When it comes to mass, what's very important is that on any planet or on any surface, mass will remain the same. Mass will remain the same no matter where it is weighed. So if you weigh yourself on the moon, you will stay the same. Okay? Your mass will stay the same. But weight will vary. Okay? Because it's calculated by taking your mass times the gravity, or the gravitational pull. So your weight on planet Mars will be different from your weight on planet Earth. Obviously, because by the formula that I just showed you, W is equal to mass times the gravity. Okay. Mass is the amount of substance of an object. So that's how we clearly define mass. It's the amount of substance, while weight is affected by the force of gravity and not the size of the object. Okay. Of course, mass, as I mentioned, is measured in newtons, while weight is measured, mass is measured in kilograms, while weight is measured in newtons. Okay, as I've already mentioned, your mass on the moon will be the same as your mass on the Earth, but your weight will be different. All right. In space, though, all right, in space, like actual open space, okay, a person may have no or little weight, and you will float, and we'll give that a certain name or term, which is weightlessness. Very easy to remember. Weightlessness. In other words, there's no weight because your mass, there's no gravitational pull. So there's no gravitational pull, there's no gravity, you have no weight. You still have mass, but you have no weight at all. Hence why you'll just float. Okay. A perfect example is having a look at astronauts in space. A quick YouTube video will obviously help you to see that. Obviously, astronauts in space, they are in the space shuttles, or what's the word I'm looking for? The satellites that are floating in the Earth, right? Some people have given up their lives to work there, and etc., etc. Thanks to them for doing that. Anyway. They are there, and if you just do a quick YouTube, you'll see that they are able to walk upside down. They're able to walk on the side. They're able to, if they don't want to walk, they could just float from one door to the other. Okay, because of the weightlessness. They have the same mass as when they are in this as when they are on the Earth's surface, but their weight is either zero or very little, because they are very, very far from the Earth's gravitational pull. Okay, a quick YouTube video of that. There's a couple of good videos to demonstrate how those astronauts obviously live when they are in rockets or space shuttles, as they call them, or wherever they are, or at a space station. All right, or at a space station. Okay, some funny photos that they always send through back down to Earth, etc., etc., about some foolishness that goes on, because they really have a lot of fun. You can really do whatever you want, because you have very little or you have no weight. Okay. Thank you, grade 9s, for joining me this evening on our session today on forces and we've looked at contact forces, all of them, and at non-contact forces, only looking at the gravitational force. If we come back next week, we'll be having a look at magnetic force, and hope to touch on and get through electrostatic force.